Hello and welcome. In this video I will be covering the primitive data types in Solidity, also going over variables, constants, and immutables. Just a quick heads up before we get started. A lot of the content from today's video comes from the Solidity Documentation as well as the Solidity By Example page. And I did add some additional content of my own as well and some comments. So in case you wanted to grab the code from today's video, you can head on over to the repository here. The link is included down below in the description. So let's get started. If you're familiar with a programming language, then probably some of this, if not most of it, will feel familiar to you. But nonetheless, let's start from the beginning here. So at the very top, we have this Boolean type, which in Solidity is declared with the bool keyword. Just like any other Boolean type in any other language, that is, it's going to be either true or false. So in Solidity, if you didn't specify the value explicitly when you're initializing it, you would actually have a value of false. So if you want it to be true when you initialize it, you have to explicitly set it to true. Next we have the unsigned integer type. Unsigned refers to just the fact that it can't have a negative sign. So therefore, it's only non-negative integers, in other words, only positive integers. In Solidity, you have many different sizes of integers, which have different ranges. So, for example, uint8 would be an 8-bit integer, and the range will always be 2 to the however many number of bits you have minus 1. So for uint8, you would have 2 to the 8 minus 1, which really comes out to 255, for example. And same thing is true for all the other integer sizes. And then if you don't declare a size for integer, uint would be an alias for uint 256. So if you just say uint 256, or if you just also just say uint, both of those will end up being the same size integer with the same range. Next we have integer type. So unlike uint, it could have a negative sign and therefore could represent both negative and positive values. The difference also in the range is going to be 1 less power of 2 basically. So in other words, if it's int 256, the range would actually be negative 2 to the 255 to 2 to the 255 minus 1. So notice how it's 255 and not 256. And also notice how for the positive values, you subtract 1 from the range, but for negative values, it's just the exact range. So negative will be exactly negative 2 to the 255. And once again, if you just say int, it's going to be an alias for int 256. This one's really handy. You're probably going to be using this quite a bit. Of course, if you want to know the range of the integer, you can always take a calculator and do, power of 2 to the whatever number of bits you have. But if you want to get that value in code, it's very easy. You just use this type function, pass in the size of the integer, and then check either the min or max property, and that'll give you the range if you need to check that in code. Next we have the address type. So this could represent either a wallet address or a contract address. And it's basically a series of bytes, but unlike the regular bytes type that I'll cover in a moment, there's a strict set of rules it has to adhere to. For example, addresses can only be 20 bytes long. So when you're declaring an address, the compiler will check to make sure it's a valid address that adheres to the set of rules that would need to be a valid address. Next, we just have the bytes type. So that's going to be basically a sequence of bytes, and you can either have fixed size bytes or dynamically sized bytes. So fixed size would be like if you're saying bytes 1 or bytes 4, etc. Dynamically sized bytes, you could have any size you want. However, I believe the dynamically sized bytes would not be a primitive data type. It would be actually a reference data type. So bytes are represented in hexadecimal. So that would be basically base 16. And if you have, for example, here this 0x56, that would be 86 as a whole number or actual integer. And this will be the binary representation of that number. So, for example, since it's base 16, the rightmost number would be 16 to the 0 times whatever number you have here. For example, so 16 or any number to the 0 is just 1, so you would have 1 times 6, and then the next number would be 16 to the 1 times whatever number this is. So 16 to the 1 is just 16, of course. 16 times 5 is 80, and therefore you get 86. And then might as well actually go ahead and quickly touch on binary representation just in case anyone is not familiar with that. So binary is a sequence of 1s and 0s, and it's read from right to left. Each number represents a bit. that can be switched on or off. So if it's off, it's 0. If it's on, it's 1. And then each bit will be a higher power of 2 going from right to left. For example, the first bit here is just 2 to the 0. So if it's on, it's going to be 1. If it's off, it's going to be 0. Of course, any bit that's off is going to be 0. But so here we have it on, so that's why this uint 8 1 would be 0 0 0 0 so on, and then just 1 at the end. If I were to change this to a 1 right here, then that would be 2 to the 1 plus 2 to the 0, which is 2 plus 1, so that makes 3. So I would change this to a 3 so it's accurate. If I were to flip one more of these on, then that would be 2 to the 2. So in other words, 2 squared. So it would be 4 plus 2 plus 1. So that would make this 7, for example. So that's how the binary representation of a number works. But anyways, let me change that back to what we had here. And then going back to where we left off with the bytes. So next we have actually just the default values. So bool would default to false, like I mentioned earlier. Any integer type would default to 0. And this is a kind of interesting one. The address is actually default to what we call the 0 address. So it's essentially a 20-byte representation of all zeros. So if anyone's familiar with the term burning, burning tokens, whatever, just to cover that as well, basically what's happening is you're not actually somehow burning the token as if it's not going to exist anymore. What's really happening is that token is getting sent to the 0 address on the blockchain, which is an address that no wallet or contract could ever theoretically have. So therefore, you're sending it to an address that's unusable, and those tokens will no longer be able to be recovered. So that's what burning is. So that's why also the 0 address is used as a default value, because that represents an uninitialized address. In other words, it's an address that can never actually be used by anyone. So that covers the primitives. Let's move on to variables. So variables can either be state variables that are stored on the blockchain and that are the scope of the entire contract, or any contract that would inherit from this contract, assuming that they're public or internal. Then we also have local variables that exist just inside a specific block of code or a specific function. So here we have a local variable, for example. But then also there's global variables in Solidity. So in the example that I copied from Solidity By Example page, they included a couple, but I added a bunch more here just so I can make sure I covered as many relevant ones as possible. So first we have block timestamp. It's basically measured in seconds since the epoch or epoch, however you want to pronounce this word. And then also we have the gas limit. So that's the total units of gas that can be used in a single block by all transactions that are being mined in that block. I think currently for Ethereum that would be like 30 million. And then we have message.sender, which is the address of the caller. I added this comment here that also mentions it can either be a contract or an externally owned account. So it could be a contract or a wallet, in other words. So for example, if you have a wallet calling a contract, then message.sender is going to be the wallet address. However, if you have a wallet calling a contract, calling another contract, then that last contract that gets called will have message.sender equal to the contract that called the contract. Hopefully that made sense. Also, we have message.value. That's basically how much ether is being sent to the function. And in order to not have the transaction revert, you can only send ether to a function that's marked as payable. If you try to send ether to a function that's not payable, the transaction will fail. And if you're on a different chain, a different EVM chain that is like Polygon or whatever it is, then message.value will be equal to the native token. So on Polygon, message.value is equal to Polygon. If it's on Binance Smart Chain, the message.value will be how much Binance whatever token was sent to that function. Next, we have transaction origin. That can only be a wallet. It can only be an externally owned account because that represents the very first caller of a call chain. So if you have a wallet calling a contract, it calls another contract, so on and so on, however deep that call chain goes, this will always be equal to the wallet that started the whole chain. Next we have gas price, so that's how much each gas unit costs in Wei, which is the smallest denomination of Ether. And then next, lastly, we have gas left. That's basically how many units of gas are left to be used or available to be used in this transaction. So I'm going to run both of these functions later so we can see all these logs just to get a sample, printout of what these values would be. But let me go over to the next function here first. So I added another function here called do something else. And here I just wanted to include the units you can use in Solidity as well. So you can use units to represent way, gwei, and ether. So usually this is used for the native token, like Ethereum, for example, because it's 18 decimal token. But in reality, actually, it can be used with any token that's 18 decimals. So as long as you know the token you're dealing with is 18 decimals, or has 18 decimals, I should say, then you can just use these shorthand representations to deal with the different denominations of that token. So that might be useful. Otherwise, moving on, another useful thing is the units of time. So you can have minutes, hours, days, and weeks. Since it's all in seconds, then there's you just, if you want to have 1 second or so however many number of seconds, you would just use a unit for that. So for example, 1 minute would be 60 seconds, so this would be equal to 60 basically. 1 hours would be 60 times 60, so that'd be 3600. So all these are just represented in seconds. And we have this little warning here that I copied from the Solidity documentation that says take care if you perform calculations using these units, because there's actually leap seconds. So if you're trying to, for example, make sure that something doesn't happen before a certain date and time that's in the future, you would have to somehow account for those leap seconds or add a buffer. So more commonly, let's say you wanted something to happen no sooner than like a year from now. Most commonly, you would add a buffer just to make sure it happens a little bit after a year rather than a little bit before a year. But even though there's leap seconds, which can kind of remove some of the precision of these calculations if you're using these units, the units will never change. This will always be 60, this will always be 3600, etc., etc. These values actually won't change. It's just that if you're trying to represent a specific point in time, then you might have to account for the leap seconds if you're really trying to be super precise about it. Okay, so maybe now is a good time to pause and just go ahead and check out some of these console logs after we call these functions. So I'm going to move over to the testing folder here. And I have a few functions that will deploy the contracts and then call the functions just to print out the logs. Just note that these are not actually unit tests, because all I'm doing is saying expect true to be true, which of course will always be true. So it's not actually testing anything, it's just to show the console logs. But nonetheless, let's go ahead and check it out. So I'm going to say npx hardhat test, and then I'm going to specify the exact file, variables.js. Okay, so here we go. So this is our block timestamp. This is the number of seconds since the epoch. This is the current block gas limit, so it's 30 million. This is the address of the caller. So here I just deployed this contract with the default deployer from ethers, so that's whatever address that Hardhat decided to give me right now. And then here's the value of the message. I guess you can see in this test right here, I'm just sending 1 ether, and then since it has 18 decimals, you have 18 zeros right here, so it's 1 ether. And then also transaction.origin is the same thing with message.sender, because there's no call chain involved, so the sender is the same as the wallet, or the origin is the same as the wallet. Here's the cost in Wei of each unit of gas. And then here's that gas left variable saying that I would have had this much, many more units of gas that could have been spent in that transaction if needed. Okay, and then otherwise, all those assertions that we had here to go from one unit at a time to the next all passed, so that worked as expected. Next, let me go over and cover the constants in immutables. So they're really similar. There's two fundamental differences. First of all, constants are always initialized right when you very first declare them. So I can't just say constant, leave it, blank, and then somehow initialize it later. That's what immutables would be for. If you wanted to have an immutable value, but not set the value itself until the contract was deployed by passing in some value to the constructor or something, then that's what you would use an immutable for. But otherwise, once you set them, neither of them can be changed afterwards. They're both, immutable. So there's also one other difference, which is constants are slightly less gas efficient. Immutables are slightly less gas efficient than constants. That's because, oops, there's a little typo here. Let me just fix that as well. But yeah, that's because immutables are not known at the very point in time when the contract is being compiled. They're only known after the contract is being deployed. So Solidity will reserve a 32 bytes spot in the bytecode for the immutable. So even if it only needs, let's say, half of that, it'll still take up a 32 byte slot. So when you're reading from it, it'll use a little bit more gas than, let's say, if you had stored that 16 byte value in a constant, for example. So other than the way you initialize them and other than the fact that the constants are a little more gas efficient, they're pretty much the same thing, though, in the sense of how they function. And otherwise, one more thing to note, though, regarding immutables is that you could actually leave them uninitialized, and then it'll forever be set to the default value. So, for example, if I run the immutables test now, we'll see that the immutable, my int got set to the value I passed here, and then my address gets set to message.sender. So let's just check that out really quick first, and then I'll show you what happens if you leave it uninitialized. So first, let me just go ahead and say hard hat test, and then I'm going to specify the immutables file. So you can see when before it was initialized, it had default value as 0, which is what it's printing right here. And then after we set my int to be equal to this parameter of the constructor, then it got set to 5. And then my address is equal to message.sender. So now if I commented this out and then ran the same test, we would see that my address is actually equal to the 0 address. Just to really drive home the point here, that once it can only be initialized in the constructor, so once you run the constructor, you have no chance of initializing it again. Just to illustrate that, we can see that if I uncomment this function that attempts to set it, we're going to get a big red error here saying, hey, you can't do that. If I try running the test, it's going to just fail to compile, basically. So all immutables must be set in the constructor, or they're forever going to be stuck on the default value. So if you ever are looking at another smart contract or something, like if you're auditing it, whatever, you happen to see there's an immutable that wasn't set in the constructor, almost certainly that's some kind of mistake that you found right there. But in any case, I think that covers it for this video. Thanks again for joining me here. I think next video I'm going to get into the reference types and continue on with more about the Solidity language. So hope to see you in the next one.